I joined the NACA at Langley Field, Virginia in June of 1957 as an aeronautical research trainee. The first 6 months of activity that I was involved with at the Langley Research Center was my assignment to a three-stage rocket program that tested drag reentry configurations. And we looked at the heat transfer and pressure distribution on these reentry bodies. This was very exciting work for me. It had a lot of physics to it, and I enjoyed that. And it was very exciting when I'd go up to the Wallops Island for these firings. So we had 3 such firings, and we were reducing all that data. And in background, there was a lot of work going on by Max Faget as to trying to select the right type of configuration for the man in space program. These were very quiet meetings. All we knew was that President Eisenhower had wanted the civilian agency to be in charge of space research and exploration, and we were very much involved with getting the right configuration for a manned capsule. And that's the term that we used, the manned capsule. Mercury name hadn't been adapted yet, and these were really what you'd call in the early days. The Air Force was interested in a hypersonic glider. Max Faget understood that that would no doubt make up just the structure about 60-some% of the total payload. And so he was focused more on a smaller configuration that could go in the Atlas launch vehicle. The Atlas launch vehicle had its first test, successful test, the Atlas A, in June of 1957. And that was only 12 days after I joined the organization. That organization was the Pilotless Aircraft Research Division, headed up by Joe Shortle, which reported to Dr. Gilruth. Underneath that was Max Faget, who headed up the Performance Aerodynamics branch. And then I worked within that organization under Bob Pilot and Leo Chauvin. And these are very, very intelligent and very efficient, effective managers and project leaders, so they were. So that went on for about 6 months. And as we went into the latter part of 1957 and early 1958, the design engineers led by Cadwell Johnson has formulated the external shape of the Mercury capsule. They knew that a man lying down inside of it would have to pull his legs back a little bit, and that would raise them above the heart, and this would make it more effective for the heart to keep pumping blood under a high G load. And the G loads at that time had a limit on what they thought man could take, which would be about 12 Gs. We had a higher parameter that was driven by the G loads by the escape rocket of lifting the Mercury capsule off of the Redstone or an Atlas while on the launch pad. In order to get far enough away, it required a G load of 18.6. And of course, this wasn't possible. It had never been done. So Faget, Bland, and I formulated what was known as a contoured couch, where a body could be lying down in a semi-supine position. The chest cavity would be supported on the sides so that it wouldn't be forced down as pressure against the heart, which would let the heart pump better blood to all parts of the brain. Very nice. It worked. We got Bob Champagne as a test subject. He was from the Flight Research Division, a test pilot. He knew all about G loadings, and so we modeled the first contoured couch after him. In the same time period, we were discussing with the people at Navy Johnsville and at Wright Air Development Center in Ohio, in Dayton, Ohio, what centrifuge we could use to make this test. It ended up that Navy Johnsville was most cooperative in fitting us into a work schedule. And so beginning in the spring of 1958, we were working towards a summer testing, which actually occurred on July 30th and 31st. And these tests were successful. It meant that our configuration could proceed. The escape rocket that would be required to lift somebody off the launch pad under difficult conditions was identified, and we knew exactly the characteristics of that. Bob Champagne and I spent several trips up to Navy Johnsville, and we became very, very comfortable with the type of test that was going to be done and the test subjects that we would have. Bob Champagne had taken rides on the centrifuge. On July 30th, we had Carter C. Collins, who was a test subject from the Navy, stationed at Johnsville Air Development Center, and he was able to go up to 21 or 20.6 Gs. And this was very, very exciting for us. The next day, Flanick and Gray did the same thing, another test subject from Navy Johnsville. And so we called all the information back, which meant that our program configuration could really proceed. The real showstopper seemed to have been taken care of. As we took the equipment out of the centrifuge, another test pilot came and sat down, and we discussed what had happened. And I said to him, "Neil, I think you should get in the space program." And Neil Armstrong responded to me by saying, "Jack, right now I have the only flying machine in town." And then he did respond to the call for Gemini astronauts, and that's when he entered the program. My first assignment after I completed the rocket launches at Wallops Island was to work with the fabrication shop to generate a full-scale weight and balance model of the Mercury capsule. It had the right curvature of the heat shield, it had the right afterbody slopes, and it also had the weight and balance so we could determine exactly how the CG was being affected as we put more things inside to represent support systems, instrumentation panels, and things of that nature. That ended up to be then used over for full-scale drop test into the water as part of determining what impact speeds we could give the capsule with the man inside, and that drove the design of the parachutes. They took that particular full-scale mock-up, used it in the drop test in the back bay, and eventually took it down to Pope Air Force Base and used it and dropped it out of the C-130 aircraft with the right cargo chutes attached. These were a series of very intense but very successful events, all of which contributed to the assurance that the approach taken with the configuration was the right approach. But it was trying to just put it on top of the Atlas and without changing the upper Atlas structure and making sure that the diameter was adequate enough for the man inside. There were some problems, and we used certain curvatures in order to warp the afterbody into the leading edge of the beryllium of the heat shield. The team began to build. We got various people looking at various subsystems within the capsule. We had people looking at the network. We had a lot of people considering the recovery operations that we'd have to bring together with the Navy. We continued to define requirements, but the level of definition in those days was quite brief. Before the RFP was released, we had an industry conference where we invited all the industry to come in and listen to what the manned capsule specification was going to be. There were 6 major presentations, and I was asked to talk about the instrumentation panels, the cockpit layout, and the contoured couch requirements. Needless to say, I was the youngest member with the least experience, and I was very concerned that what I had to say would come off properly. It did. Everybody was most courteous, and I was scared to death. Industry went off and developed their response to our requirements. We received 11 formal proposals. We asked industry to work real hard in the fall, and everybody had to work through the Thanksgiving holidays to respond to our timeline. But then we worked with the evaluation of the proposals. On Christmas morning, we had time with our families, but at 1 o'clock we were back on the job, which ran into 9 or 10 or later every night. The same thing happened on New Year's Day, but we were very, very excited about what was happening, and we were glad to put in all that extra time. Was I surprised? I was never really surprised how Mercury was going to turn out, because every step of the way we maintained the objective that we wanted to have put man in space in a safe manner, return him safely to the Earth, and studies the effect of space travel on man. We proceeded with very well-defined incremental steps. Our management insisted that we keep everything simple, that we did incremental testing, and we never left any unanswered critical parameters on the table. We kept working to ensure that when we went to the next step, we were still being in a success path. The director of the Space Task Group was Dr. Gilruth. Charlie Donlin was his deputy. We had leadership from men from the Flight Research Center there. We had our Max Faget and Cadwell Johnson, Guy Thibodeau, and all that team of people focused on it. It was a great team. And these people were well known. They were the leading technologists at their time in their areas. And it was very interesting to see how giving NACA, which became NASA, a role in space, a lot of the research people felt that we shouldn't get into operations, that it was always the history, that the operations part of it would be done by the military or the contractors. And I even had one very renowned individual come and talk with me one day and said, Jack, you really don't want to get into that space program because I'm not so sure that it's going to go anywhere. Well, after working on ICBM reentry warheads, I was glad to put that technology into the peaceful use of outer space, and I was just delighted to be selected to be in that original 35 members that was asked to focus full time on the space program, the manned spacecraft program. I think we were all excited about being part of the project. If you look back on what we thought was ahead, we thought we could almost do those things. But we really didn't understand just the depth and the size of the undertaking. We thought these were our original budgets. We started out to do Mercury at about 110 million, and it took a little bit more than that. But the cost of the programs in those days were not nearly as great as subsequent programs to follow. And bear in mind that we were using solid rockets for testing in the Little Joe program that was already developed by the Army. We were using liquid-fueled rockets that was developed by the Air Force and the ICBM world. So a lot of the expense R&D had already been put in place, and we just captured that in order to man-rate it and make sure that all the subsystems and modules work together in a proper manner. We felt that the complexities that the Atlas had gone through, some of the spectacular failures on the launches from the Cape, they discovered what caused the problem. They worked and recovered the deficiencies and made it sound, and they went forward step by step. So we had a program that was running in parallel with the boosters. We had recovery operations which were being established by the Navy. We had people focused on the worldwide network that would be required. We had started and had a plan to launch 6 to 8 Redstone rockets. We ended up only launching 2. We felt we had achieved the objectives of the program after the second launch of a manned Redstone flight, which was Gus Grissom, who followed Al Shepard's in the first flight. And then we were ready to put all of our attention onto the Atlas program. Everybody in the office was knowledgeable of what was happening. We first started out to baseline a beryllium heat shield. We had made tests with beryllium. We had made tests with ablation. The contest between what would be selected continued for some months. We actually did make a full-scale beryllium test, but it ended up that the heat sink would put a lot more heat energy into the capsule and would continue to do so following landing. That was one of the reasons that we were able to go to the ablation heat shield and use more ablative material. The ablative material would, once it began to heat up, would eventually then flake off, and that by the flaking off of the ablation material would take heat away then from the structure, so that when it landed in the water, that it would not continue to heat up the insides of the capsule like beryllium would do. Beryllium was also heavier, and for some people responsible for weight and center of gravity requirements, they selected ablation much earlier than others, but they ended up to have made the right early selection. There was a lot of testing of ablative material in beryllium for reentry ICBM activity. Basically took all that technology data and applied it to the Mercury capsule and to how it would fit on the Atlas. Well, as McDonald won the contract to build the Mercury capsule, and we all worked on the requirements and the specifications very, very closely with the contractor teams, and that resulted in everyone being very, very familiar with all the subsystem requirements, all the progress being made with the manufacture and the structure, the issues coming up with using beryllium heat shields on the afterbody and things of that nature. And I then was assigned the responsibility of following a Mercury capsule to take it into the Marshall Space Flight Center and putting it on top of a Mercury Redstone launch vehicle and doing static firing in order to evaluate the acoustics and the vibration We didn't have a man in the Redstone when we made the test, but we had all kinds of instrumentation. And we were able to prove what we all thought was going to be true, was that the acoustic noise would not harm an astronaut with his helmet inside the capsule during launch. That he would be able to communicate effectively, he'd be able to hear what mission control was saying, and that all ended up to be a good test, a solid test, no surprises. It's interesting to review the size of the Space Task Group. The 35 members that were asked to begin the program in the fall of 1958, on November the 5th. That was a key milestone. When we launched Al Shepard on May the 5th of 1961, we had 256 members of the team. Now, our team was really supplemented by a lot of additional people from Langley Research Center, Cleveland Research Center, Ames Research Center, Edwards Air Force Base, all NACA installations. But still, it was a team of 256 that were there the day that Al Shepard launched. And then when John Glenn went into orbit, we had about 900 and some. So we did. And the team then was moved after the Gemini program was announced. No, well, let me go back. Al Shepard flew on May the 5th of 1961, and then President Kennedy on May 25th of 1961 announced that we were going to the moon. That was our next challenge. We had just flown a 15-minute ballistic zero-G flight, and now we were being asked to go to the moon. And I was with Dr. Gilruth in his office when that announcement came out, and he openly wondered, could we possibly go from a short ballistic flight to the moon, and by the end of the decade? That was a tremendous challenge. And could we really undertake it? In the infancy of space exploration. That led, of course, to why we needed the Gemini spacecraft. And so the team had to build another team to start looking at Gemini as we got into the early Apollo requirements. And the Apollo requirements drove the Gemini to be able to do rendezvous. It drove us to be able to handle 2 Gemini launches in close proximity from the Cape in order to prove these things. A lot of interesting problems which people took on that had no solution to them, but their hard work brought it all together in a successful manner. Again, the test requirements were fully understood, incrementally going from one test to the next test objective without not understanding all the parameters. All this came together with a very hard-working team that was very, very disciplined in the NACA tradition.